Okay, so the second speaker of this afternoon is Radu Ignat from Toulouse, and he will speak about maximum principle and applications. Radu, please.
Yeah, thank you, Mihai. So it's a pleasure to give this talk about the maximum principle and applications. So the maximum principle is one of the most used tools in partial differential equations in order to prove uniqueness of solutions. Okay, so the aim of this talk is to give you a flavor on this principle. So first I will state it in 1D for convex functions, then we will try to generalize it in a higher dimension and to a larger class of functions, and then we will see some applications like uniqueness to PDEs, elliptic PDEs, and maybe some symmetry results and Liouville type theorems. Okay? So let us start. So the starting point is this observation for 1D convex functions. So the starting point is the following. So if you take a function that is I call U from 0, 1 into R, that is continuous and convex, then the maximum of this function is achieved at the boundary. Right, so it's either in 0 or in 1. Right, so if you make a picture, you see that at least the geometric interpretation is natural, right? That if you take something convex, then the maximum will be here and here, right? And the proof is just to use, so you take 2 points, x and y, and you will just see that if you take an intermediate point there, that is a combination of y and x, right? You use the definition of, right, so that's the proof. You use the definition of the convex function, and you see that this is less than the maximum between ux and uy, right? So then the maximum it's either here or there. Okay. So this is called the weak version of the maximum principle. So in the following maximum principle, I will just denote it by MP. Right, and this will be the weak version of the maximum principle. So the strong version that we will see also in the following, in a general setting, is that imagine that in this case the maximum is achieved in an interior point. How f should be? Constant. Exactly, right? So that will be the strong maximum principle. Fine. So maximum principle goes with minimum principle. So for example, if you think to minus u, then if you take a concave function, then the minimum of a concave function is achieved also at the boundary. Okay. So then the question is, what is hidden behind the notion of convexity? Well, if you think to a C2 function, so a smooth function, convexity means that the second derivative is positive, right? So it's a differential inequality. Okay? So that is how, for example, you can generalize things in higher dimension. So a remark. Right, so if U is C2, then saying that U is convex is equivalent to say that U second is positive in the interior. Okay? So this kind of maximum principle, you can generalize it for convex functions in higher dimension, right? So also true in higher dimension. If you take a domain in Rn, right? So then saying that U is convex, so convex and let's say smooth, C2 is enough. Then this is equivalent by saying that the Hessian is a positive semi-definite form. So right in the interior of omega. So in other words, all the eigenvalues, right, which are real because it's a symmetric form, they are non-negative. Okay, so you have the same thing. So we will generalize this. In fact, you don't need to have such strong condition. It's enough to look only to the Laplacian, right? So the Laplacian will be maybe the fundamental object in the following. So the aim is to generalize the maximum principle to a larger class of functions. So these functions will satisfy some differential inequality. Okay? So, and as I said, the fundamental object will be the Laplacian, which is, in fact, you don't need the full information on the Hessian, you just need the information on the trace. So it's like the sum of the eigenvalues. Okay, so this is, if you take second partial derivatives like this, right? Okay, so the first who works in this direction, taking the Laplacian, was Gauss in 1830. So he worked on harmonic functions. Then Liouville came later with a different approach using complex analysis. And finally, like 100 years later than Gauss, was Hopf that came with the modern approach that I will explain in the following. And he was capable to treat second order elliptic operators, linear operators, that can be written in the following form. So second order elliptic operators. That I will denote it by L, and that are written like this. So I will take in this form. You can do it even more general, but let me focus here on this on such form. So such operator comes in many models: physics, chemistry, biology. So, for example, if you think to chemical reaction, you will be like a chemical substance. So the Laplacian will represent like the diffusion of this substance. This will be the transport term that say how the flux goes from a higher concentration to smaller concentration, and that is the reaction term. Okay, so each term has a meaning. Physics, depending in physics or depending on the model you study. Okay, so the idea will be to see if, right, instead of taking this differential inequality, if we assume this more general inequality, can we still say that the maximum is achieved at the boundary? Okay, so always in this theory you should think to a convex function and then to say, can I generalize it to this form? So let me give you the first theorem, which is the generalization of what I presented before. So this is the weak maximum principle. So here omega is an open and bounded set in Rn, and I take u, a smooth function that is continuous up to the boundary. And so first I will say that C is 0. Okay? So I will just take B to be continuous. So B is a vector, right? So it's with values in Rn. And such that you satisfy this differential inequality pointwise, right? U is smooth enough so you can speak about the second derivatives in any point, right? Then you have the same conclusion that the maximum, so of course it's a continuous function up to the boundary, so it's a compact, so then the maximum exists and it is achieved at the boundary. Okay, so again, this is like the easy case when we don't have this zero order term. So here C is 0, and we will treat the case C different than 0 later. Okay, so let me give you the proof of this. Are there any questions up to now? No? Mathieu, tu me dis si jamais à Montpellier. Okay. So let's give the first. So the proof. So the proof goes in 2 steps. So in the first step, I assume more than that. I will assume that the inequality is strict in any point. Right? So this is okay. So L of u, so C is 0 here, right? So we don't have that. So Laplacian u plus dx grad u is strictly larger than 0 in omega, and then in step 2 we will treat the general case. Okay, so let's do the step 1. Okay, so it goes by contradiction. So assume. Let's take x0 a maximum of u in omega, right? So this exists, and assume by contradiction that this point is in the interior. Okay, otherwise it's on the boundary and it's finished. Okay, so now you have a maximum point in the interior. So what do you know? What is the gradient in that point? 0, right? A maximum point is a critical point, so the gradient is 0. So gradient of u in x0 is 0, right? Okay. So now it's a maximum point, right? So in a maximum point you have something like this, right? So this means that in any direction you go, right, the eigenvalue should be less or equal than 0, right? So So you have also that the Hessian is a negative semi-definite form, right? So in particular, the Laplacian, which is the trace, is less or equal than 0. But then you have a contradiction, right? Because if you put everything together, right, this is less than 0, which is strictly less than your operator, what you assumed there, right? So again, C0, right? So that's a contradiction. Okay. So this means that that your maximum should be at the boundary, and this is what you wanted to prove. Okay, so let's see how you do the second step, where you have that also equality may happen. So here the idea is to construct barrier functions. Okay, so the idea will be to construct a barrier function, which is what? Which is a function phi that satisfies this strict inequality. So construct phi a smooth barrier function such that Laplacian phi plus bx grad phi is strictly positive in omega. Assume you construct such a function, then what you do? Well, for every small epsilon, you will consider u epsilon to be u, so your u in the hypothesis, epsilon phi. Okay? So clearly, right, this u epsilon satisfies the strict inequality, right? So you will have that. So always here C0 is strictly positive. So then you can apply the first step. So you know that the maximum of u epsilon is achieved at the boundary. But also, right, when so since this is bounded, these functions converge uniformly to u, right? So if you have uniform convergence, right? So in an infinity, then we have that the maximum converges to the maximum of the limit. And you are done. Okay. So the only thing that remains to clarify is how do you construct this barrier function? Okay. So the choice of phi, it's an exponential in one direction. So it will be of this form, lambda x1. So only in one direction, where lambda is a positive to be determined. Okay, so you will determine in such, so write it smooth as you want, and you will be determined in order that this is strictly positive in omega. So then you have to compute the gradient of phi. So since it sees only x1 variable, what's the gradient? So it will go in which direction? E1, right? So it's equal lambda phi of x E1, right? Okay. So now you take the Hessian. So in the Hessian, again, when you differentiate again, you will just see the first entry. So that's lambda squared phi of x. And is a matrix that is 1 in the first entry and 0 elsewhere, right? So now when you write whose L of phi, so what do you have? So it is the trace of this. So that's lambda squared phi of x plus this times b of x, right? So you see only the first component of b. Right? So that gives you lambda, so it's lambda phi of x. Okay, so this is strictly positive. And then you will get lambda plus b1 of x. So this is larger than lambda minus the maximum, b is, or supremum, yeah? So anyway, b is bounded, right, on omega. So this is strictly positive, provided that lambda is strictly larger than the maximum of b, right? So the L infinity normal. So you are done. Okay? So you see, okay, so we were in this situation, so you see that this is much more general than asking that the Hessian is a positive definite form. And you still have the same result. So as for convexity, so convexity concavity, so you have the same thing if you reverse the sign. Okay? So let me give you some remarks. So the first one is, do you have questions? Please ask.
What is the notation E1, E1, E1?
This is right. This is the first direction. So E1, En is the canonical basis in Rm. Is the basis in Rm.
And when you write the product,
So this is a tensor, if you want. So it's the matrix. Yeah. So this is the matrix 1 and zeros all over. Okay. So the first remark is that if you reverse the sign of your operator, so if you think instead of u like minus u, right? So then you will have that if this is negative in omega, then the minimum of v is achieved at the boundary. Okay. So again, v is C2, C0 up to the boundary being the same class. Okay, and if you put them together, then you will have that if Laplacian u plus bx grad u is 0, then you know that the maximum and the minimum are at the boundary, so this means u is between these two values. Okay, so u will be between the minimum at the boundary and the maximum at the boundary. So this is what it will give you the uniqueness, for example, in some linear boundary value problems, elliptic problems. So this will give you, like, to prime the uniqueness result that I was mentioning. For PDEs. So the result is that there is at most one solution, u that is C2 in omega, continuous up to the boundary. So solution to the following boundary value problem, which is Laplacian u plus dx gradient u is equal with some data f in omega, and u is g at the boundary, right? For some data f from omega to r and g from the boundary to r. Right? So how do you prove this? Well, you assume that there are two solutions and you take the difference, right? So you will use the linearity. You will use the linearity of your operator, right? So it's a uniqueness. I'm not speaking about existence. So if U1 and U2 are two solutions, then V, which is the difference, will satisfy satisfies the remark 2. So and more than that, right? Both they have the same boundary value, so this means V is 0 at the boundary, right? So the maximum is the minimum is 0, right? So this will tell you that V is 0 in omega, okay? Because at the boundary it's 0. So this will give you that U1 is U2 in, okay? Okay, so now another consequence is maybe what you saw in your complex analysis course is the modulus, the maximum modulus principle, right? So imagine that you have a holomorphic function that let's say that is continuous up to the boundary of your domain. Then what you saw is that the modulus, the maximum of the modulus, is achieved at the boundary. Right? So how can we get this thing as a consequence of this? Well, we just use that the modulus squared is a subharmonic function. Okay. So a third consequence is the weak maximum modulus principle for complex functions. So that's a 2D thing. So if f is defined on let's say open bounded setting in R2 from the complex plane that is holomorphic, and so holomorphic in omega and continuous up to the boundary, then the maximum of the modulus is achieved again at the boundary. Okay. So, right, in order to see that the square of the modulus is a subharmonic, well, you should recall what is the property of a holomorphic function, right? So a holomorphic function, so it's complex differentiable, right? So if you think in terms of, right, C is like R2, so it's like R2 differentiable plus something more, which is the Cauchy-Riemann system. So in other words, is that the real and imaginary part of f are harmonic, and in fact they are conjugate harmonics. Okay, but anyway, we will use only that they are harmonic, it's enough. So the proof is that, so f, you can write it like this, right? That you could see, so this is complex, this is R2. So being holomorphic means that the components are harmonic, right? And then when you compute the f squared, so now you will use the R2 scalar product, so that's R2 scalar product, right? And then this is what is 2 times f R2 scalar product Laplacian plus 2 times gradient f squared. Okay? But, right, I mean, since these are harmonics, this is 0, so this term is gone, and you have that this is positive. Right? So now you apply the theorem, and you get that the conclusion, right? Okay? Do you have questions? Okay, very well. But this was the easy case because we took out the zero order term. Okay, so let's put the zero order term and see how the difficulties come to play. So now the question is, what happens for the operator L with C non-zero? So, in fact, what will play a role is the sign of C. Okay, so let's see. So imagine that C of x is negative. So let me take an easy example. C of x is minus 1 in 1D. Okay, so let's take minus 1, 1. Okay, so so we will look to the operator, which is u second, b0, so C of x u, okay, so that's minus u. So you can cook up a solution, so a solution, you can have in fact a concave solution, right? So if you have a convex, then you think to minus u because it's linear, right? So you have a solution u which is concave, which is, right, so if you think to the solution of this is u second minus u equals 0, so u is like exponential minus exponential, okay? So that's why I take this, so it's exponential x plus exponential minus x. I take this one, so this is a concave function. So of course, if I take something concave, of course I cannot expect that the maximum is at the boundary. Right, so what is this function? Right, so in 0 I can compute it, is minus 2, and then it's concave, right? So it's something like this. Right, it's an even function, it's something like this. Right, so this you will not have that the maximum of u, right, it's at the boundary, right? Right, because it's in the interior. However, there is something that remains true, is that if u is negative at the boundary, then u will stay negative inside. Okay? I write it like this because I will generalize it in higher dimension after it. Okay, so this is true. So in fact, this is something that will remain in general, provided that the sign is negative. So this is what I will tell you in the following. And let's see now the opposite sign. So plus 1. So then L of u is u second plus cxu, so that's a plus, so the solution is like sinus and cosinus, right? So then a solution, at u equals 0 is u of x, it's like sinus of 2 pi x. Okay, so maybe it's better to take, okay, I took it in, okay, let's take it in 0 to pi like this. I won't change this. Okay, so then it's the sinus. Okay, so what's happening with this solution? It changes sign, right? So this means that the maximum, neither the maximum nor the minimum are not at the boundary, right? So this will tell you that you cannot have this, right? So this does not imply 1, and this does not imply also this, right? So even this is wrong. So that's the bad case. So now, the theorem, the general theorem. So you see that if C is not 0, then you cannot expect what we had before, but this is still enough for uniqueness in general, right? You can do some comparison principles. So theorem 2. So it's the weak maximum principle for C negative. So again, if you take an open bounded set, you in C2 omega continuous up to the boundary, B C0 up to the boundary, vector field, and C scalar such that C is negative, and LFU, so it's our operator, is positive. Okay, then you will have that 2 poles, right? So this means that if U is negative at the boundary, then U stays negative in omega. Okay? So the proof goes like in the previous theorem. So you will have 2 steps. So we will assume first that this is strictly positive, and again playing where the maximum, if there is a positive maximum, what can happen. So it's by contradiction, and the second step, you do the general case, and again here this is based on constructing a barrier function that is smooth all over, that is strictly positive, but you have to be careful that it is also less or equal than 0 at the boundary. Okay. So I let you automate. Okay. So now, what is maybe more important is, because this is weak maximum principle, is to go towards the strong maximum principle. Okay? So let's see what is the main ingredient there. And this main ingredient is in fact the remark of Hopf that is very important, is how the derivative behaves at the maximum point at the boundary. Okay, so towards the maximum principle. So the strong. So let us consider that we are in a ball in Rn. Okay. So if we are in our hypothesis, okay, we expect that the maximum is at the boundary. Okay, so this means that your function is like, so if you consider that this is like the maximum level set, your function is like below. Okay, so you should consider that the maximum is, the function is below, and it goes to a maximum point in x0. Okay. Then, of course, if you look to what's happening on the points going to x0, your function in that direction increases, right? So you expect that the derivative here is larger than 0. Okay. Okay. So let me write this. And so assume that x0 at the boundary satisfies so it's larger than what any point inside, right? Then you will have that that in this direction, so u of x0 will be larger in particular than u x0 t mu, right? So any point in this here, right? So here mu is the normal, external normal, unit normal at x0. So this means that the derivative in that direction is larger or equal than 0. Okay? So here there is no differential inequality on u or anything. So Hopf discovered that if u is a solution of that differential inequality, then and if x0 is a strict maximum principle, then this is strictly larger than 0, and that's fundamental. So that's the Hopf lemma. So from now on, I won't consider the case C. So I will consider the case. So from now on, I always work with C0. I don't want to go into troubles, but you have theorems for that. So Hopf's lemma, it's telling you that if you have a function, let me consider C2 up to the boundary, x0 at the boundary, a maximum point, and L of u, so which is the Laplacian dx grad u, that is larger or equal than 0 in B. Okay, so again, B is C0 up to the boundary. Then, what you win here is this strict inequality. Okay, so that's fundamental. So I give you the a reference. So the book of Han and Dean of elliptic PDE, and you go at page 26. Okay, so let me show you how, thanks to Hopf's lemma, you can prove the strong maximum principle. So this is like for the convex function, if the maximum is achieved in an interior point, this means that your function is constant. So, so theorem 3, strong maximum principle, so again C0 here. So let's consider omega to be bounded, open, and connected and u that is C2, C0 up to the boundary, and L of u is Laplacian u plus Bx grad u that is larger or equal than 0 in omega. So if u achieves its maximum in omega bar in an interior point, then u is constant. So how it goes? So let me sketch the idea of the proof. So let us say that m is the maximum value of u. And assume that by contradiction, that u is not always m. So this means that in your domain you have points where u is less than m. So, right, you have that this is x0 where u is m. So you know that the maximum, you have also maximum points at the boundary, right, by the weak maximum principle. So maybe the set where u is m is something like this. But you have also that the set where u is less than m is not empty, right? And u is continuous, so this means that it is open. So if you want to make it short, you could hook up like a ball B that is in the set where u is less than m. So in this ball, you are exactly in the conditions of the Hopf lemma. So if you take this point like x1, okay, so you will have that like so x1 it's like the boundary intersection with the u equal m, okay, and you can apply the Hopf lemma, right, because that will be the maximum point inside, strict maximum. So there you will have that in this direction u, du nu in x1 is strictly positive. But on the other side, x1 is a maximum point. So that's a contradiction with the fact that the gradient of u in x1 is 0. Okay? So this means that your u is always the maximum. It's always a constant. Okay, I make it quickly, but at times runs fast. Okay? Questions? Okay, so very well. So I showed you the weak maximum modulus principle. So let's see the strong maximum modulus, right? So complex analysis, so corollary. So the strong maximum modulus principle. So again, we take f to be a holomorphic function from a domain. And again, this domain should be connected, right? Because if it's not connected, then you could have different constants, etc. So omega is open bounded connected. Okay, and f is continuous up to the boundary. Okay, so again, if the modulus achieves its maximum inside, then the full f should be constant. So not only the modulus, the full f should be constant. So if the modulus achieves its maximum in an interior point, then the full f is constant. So how you see this? Well, you should just recall that when we compute the Laplacian of f squared, that was 2f dot Laplacian f, which is 0, because f is holomorphic, plus 2 times the gradient of f squared, right, which is positive. So there we could apply this, right? So now you apply the strong maximum principle for modulus of f, and you get that modulus of f is constant, right? But what does it mean? It means that this is 0. So it means that the gradient of f is 0. So this means that f is constant. Okay. Okay. So yeah, because I want to go a bit to tell you about Liouville type theorems, right? So in the same perspective, when can you expect that a certain solution is constant of a PDE, and also to give you a symmetry result that we like particularly in this institute. So let's. Do you have questions? Okay, so Liouville theorem, and then so let me just state these results, and then you can go to questions. So, the theorem of Liouville, which is based on harmonic inequality, but I don't have time. Of course, there are also some other ways to prove it. So for harmonic functions, it's easy because you have the mean value formula, but okay. So if omega is is the full, let's take the full space, Laplacian u is 0, so it's harmonic. And you know that u is bounded either from below or from above. Okay, in Rn, then you get that u is constant. Okay, so there are different ways to prove it. Either so harmonic functions, maybe you saw that you have a mean value formula, so you can use that and use the derivatives and get thanks to the fact that u is bounded, that the derivative should be 0. Right? But there is another proof using harmonic inequality, which is in some sense a quantitative way to for the maximum principle. Okay? So let me just give you so for the proof. See again the book of Han and Lin. Is the corollary 1.27 at page 14. Okay, and now I go to a symmetry result, and I finish. 2 more minutes. Yeah. Okay, so a symmetry result. So symmetry of solutions to some. So here I do some non-linear elliptic PDEs. So I will consider the ball. So this is a famous theorem due to Guidas-Ninirenberg. Guidas-Ninirenberg. So I will assume I am on the unit ball. unit ball in Rn. And I assume that U is a C2 solution continuous up to the boundary. Okay. Solution of the following nonlinear. So see, here it's something nonlinear, I will explain. In the ball, U is negative on the boundary, sorry, inside, and 0 at the boundary. Okay? Where, so since I restrict only to negative solution, I can say that this F is defined only on negative things, and this C1. So then you can prove that such a U is invariant with respect to any rotation. So in particular, it's a function that depends only on the radius inside the ball. So this is a symmetry result. So then U is symmetric in the sense that U is invariant with respect to any special orthogonal matrix, right? Which tell you, so in particular, U is a function that depends only on the radius, and so your V is increasing. And V prime is increasing, strictly increasing in 0. Okay? And only one word about how you prove it, so why the maximum principle is essential here. So this is what is called the moving plane method. Let me explain to you. So the proof. So it's the moving plane method. It's very geometric. So this is your ball, okay? So what you do is that you start with the plane, with the hyperplane, okay? You take a hyperplane and you go till you touch your ball, and you go a bit further, okay? So let's say that your hyperplane is here. So what you will do is that you will compare the value of your function here with respect to the symmetric one. Okay, so you will compare what is the value in this point x0 with respect to this point x lambda, right? Because let's say that you achieve here some lambda. And then you will prove that the value here is less than the value here, thanks to the maximum principle. And the aim is to be able to push this hyperplane till you touch the origin. So if you touch the origin, it means that the value here will be higher than the value here. But then you can do the things in the other way around, from the other direction. So then you will get that this is also higher than that. So this means that the value here and the value here are the same. Okay. So this, in other words, it means that on each sphere, if you look to the point symmetric with this plane, you have the same value. But then, of course, then you will say, okay, but now if I take some arbitrary sphere, I look to 2 points. I want to prove that the value here is the value here. Then what you do? Well, you just take a hyperplane that is orthogonal to this one, and then you apply this moving plane in this direction, and you get that the value here is the value here. So this means that on every sphere, your function do not move. Okay, so that's why you get this. Thank you.
Thank you very much, Radu. Thank you. Are there questions or remarks?
Merci beaucoup pour l'exposé, il n'y a pas de questions ici.
Ok.
Pas un peu de questions ici, Radu, ouais, merci.
Bon, merci.
Yes.
Can you repeat is there some geometric intuition for the Hopf lemma? And I missed it maybe.
Yes, yes. So for the Hopf lemma, okay. So the thing is that if you have, what was the point? Your function inside, so imagine that this is like the level 0, okay? So this is like the level 0 of your function here, okay? And your function u is less than 0 inside, okay? So if you look in this direction, so yeah, so this is the maximum level. So your function is strictly increasing, right? But it could also happen that the derivative is 0, right? So imagine that you have some function like this, right? Imagine you have it like sinus or cosinus, right? So here the derivative could be 0, okay? So you have a strict thing. So the first thing is just to say, well, here it's increasing, so the derivative in that direction is larger or equal than 0. But the thing is that if your operator is coercive, so you have this Laplacian playing the role, then it means that this thing cannot happen. Okay? So you should be strictly increasing. So in what so if you take only the Laplacian, then of course you can play by adding the first order term. But for example, such situation can happen in the case I was mentioning when C is you remember when C is -1. Okay, so I take the example minus ex plus e minus x. Okay, so imagine that you restrict your function to 0 minus 1 plus 1. Okay, so there you cannot have Hopf lemma. But this is because the Hopf lemma, if you want to apply to a case where C is not 0, you should apply it provided that the maximum is positive. Okay? Because again, you have the weak maximum principle, so you know that you should stay below 0. But so if you really want to have also the strong maximum principle, so this Hopf lemma, then you should you cannot apply it here because that would be wrong. But that will tell you that if the maximum would be positive, then this is still true. Okay. So let me tell you. So this kind of symmetry questions. You see, here always u was scalar. So when u is scalar, you can play with this maximum principle. But when you go to the vectorial case, so when you have a system of PDEs, that's largely open. So yeah, in Toulouse, but also in some other places, even in Montpellier. So a lot of people work in this direction. So how to get symmetry for systems of PDEs.
other questions? If not, let's thank Radu again. Just a remark, so there are many applications of this maximum principle. Well, just near Nuremberg, I think it was one of the first interesting application. It started with Serene, and a couple of years before he was near Nuremberg, and he studied a problem arising in potential theory, and he deduced not only the symmetry of solution, but only the symmetry of the domain, I guess.
Of course, right? I mean, if you want to apply some group action, then better that also your domain satisfies.
In fact, he studied an overdetermined problem, so he had Laplacian with 0 in some domain. He had an information on the u on the boundary, but also on the normal derivatives. The normal derivative of u is 1, constant equal to 1 on the boundary, and u is 0 on the boundary. Then not only, and a priori you know nothing about the domain. Well, if this happens, necessarily the domain has to be a ball, and the solution has to be radial.
Yes.
Yes, quite interesting. I think that was the paper that really inspired Girard and Nuremberg to put their symmetry result later.
Yes.
Anyway,
Okay. I think we
thanks
have
again.
cookies.
Yep.
We have cookies. We have
Thanks
coffee.
again, Radu, and well, there is a coffee break.
Yes.